Today we're looking at theoretical probability, and the word theory's in there, and that will play a part. We'll look at the definition in a minute, but really the goal is for you to be able to estimate probability using theoretical methods. And we have some vocab. So we've got equally likely, theoretical probability, fair, tree diagram, mutually exclusive, and disjoint. Probably I would say the tree diagram, fair, and equally likely you've probably heard of before. The others maybe not yet. All right, so in our first paragraph, it's in the first slide, when the outcomes in a sample space have an equal chance of occurring, the outcomes are said to be equally likely. The theoretical probability of an event is the ratio, there's that word ratio again, of the number of ways the event can occur to the total number of equally likely outcomes. So another way to see this, it's the same definition, it's just in fraction form so that you can see the part and the whole, which means it could be written as a fraction, a decimal, or a percent. Okay. So a coin, a number cube, or other object is called fair if all the outcomes are equally likely. I don't know if you've ever heard of a weighted number cube, or they say a weighted die. You could also have a weighted coin to where a certain number comes up more than others, or one side, the heads or the tails, comes up more than others. But they have to be fair. So we've got an experiment that consists of spinning this spinner once and finding the probability of each event. Now we're going to assume this spinner is fair. One of the things means that all these would have to be, all the spaces have to be the same size. And we're going to say, yes, they are fair, and assume that unless said otherwise. So the probability of spinning a 4, well, there's only one 4, and there's 5 equally likely outcomes. So that's going to be number of outcomes for 4 over 5, which is 1/5. Percent, that would be 20%. You could multiply by 20 over 20. Okay, probability of an even number. Well, we've got 2, 4, and that's all. So that's going to be 2 out of a possible 5, or 40%. And then an odd number, well, there's 3 odds, 1, 3, and 5. So that's going to be 3 out of 20, which could be the same thing as 60%. Sorry about that. All right, the next example, we've got an experiment that consists of rolling one fair numbered cube and flipping a coin. Find the probability of each event. So there are 2 different events here that you're supposed to find the probability of. And one of those events is the probability of rolling a 5 and then flipping a head. And then the second one they want you to find is the probability of an even number and a tail. The roll of the coin, or the roll of the die, the flip of the coin. So first thing we're going to have to do is show the sample space, all the different things that could happen, all the equally likely outcomes. So if we want to know how many possible outcomes there are in a sample space, a tree diagram is probably the easiest way to go. So if you've never seen this before, you're going to start out with all of your the things that could happen first. Okay, so when you roll a coin, you could have a 1, 2, 3, 4, roll a die, or a number cube. 1, 2, 3, 4, 5, and 6 are the different outcomes. Now, after that, you're going to flip a coin. So what could you flip with the 1? Well, you could flip a head or a tail. So there's 2 different possibilities. So you'll say 1 head or 1 tail, 2 head or 2 tail, 3 head or 3 tail, 4 head or 4 tail, and so on. So there are 2, 4, 6, 8, 10, 12 different things in your sample space. You can list them out, but they're pretty easy to see right here. There's 1 comma H, or you could have 1 comma T. All right. So if you did list them out, though, there they are in the same order, 1 head, 1 tail, and so on. And then there you can see that there are 12 different things in the sample space, 12 possible outcomes. And we want to know the probability of rolling a 5 and then flipping a head. Well, there's only 1 5 head here out of 12, so that probability would be 1/12. Now, if we go back and look at the probability of an even and a tail, well, I've got 1, 2t, 2, 4t, or 3, 6t. So there are 3 out of 12 here. And so that's going to be 3/12, which reduces to 1/4. Or you could look at that as 25%. All right, so now we have another experiment that consists of flipping 2 coins, find the probability of each event. So the first one is find the probability of 1 head and 1 tail. So I have, and I'm going to hold this up here, I have drawn out a sample space. Let's see if you can see that. There we go. Okay, so this is check it out 2B, the one on your thing, on your slides there for your notes. So in one flip we have a head, and the first flip, I'm sorry, so that's right. I know I'm not holding that very well. There we go. So you could get a head or a tail. Then in the second flip you could go head head, head tail, tail head, or tail tail. So I listed them out in the sample space here. And we want to know, it says up here, 1 head and 1 tail. Well, 1 head and 1 tail doesn't say what order. We have 2 of them that are 1 head and 1 tail. So that would be 2 out of a total of 4. So let's see here, whoopsie. So 2 outcomes, so that's going to be 2 out of 4, or 1/2. Okay, now the probability of both tails. Well, let's look here. Okay, the only thing we have with both tails is tail, tail, so that's 1 out of 4, or 25%. They don't even put the 25%. Okay, so then one of our other vocabulary terms is mutually exclusive or disjoint. They mean the same thing. So 2 events are mutually exclusive or disjoint if they cannot both occur in the same trial of an experiment. Be like an impossible event. For example, rolling a 5 and an even number on a number cube. You can't do that. You can't roll a 5 and at the same time roll an even number, because 5's not even. So they're mutually exclusive events because they can't both happen at the same time. So 2 things could happen if you have 2 mutually exclusive events. First of all, if you take the probability of both A and B, they'll both occur at the same time, well, that's impossible, so it's going to be 0. But if either A or B would occur, if either you rolled a 5 or an even number in that way, then you would take the probability of the first one, probability of the first situation, plus the probability of the second situation. So for up here, rolling a 5 would be 1/6. Rolling an even number would be 3/6. So that would be, wait a minute, I'm sorry. Even number would be, 3/6, and 1/6. So that would be 4/6, or 2/3. But we're doing a different one. Okay, suppose you're playing a game in which you roll 2 fair dice. If you roll a total of 5, you will win. If you roll a total of 2, you will lose. If you roll anything else, the game continues. So basically the game is over if you roll a 5, total of 5, or a total of 2, you lose. So either way, the game ends. What is the probability that the game will end on your next roll? All right, well, those are 2 mutually exclusive events. You're either going to roll a total of 5, or you're going to roll a total of 2, or you're going to roll something else. Okay? So they're mutually exclusive, so you're going to add the probabilities of rolling a 5, or a total of 5, and getting a total of 2. So we got to create a sample space. So we're going to make a tree diagram, and again, I've done that on a piece of paper. So if we look at this one, okay, our tree diagram, which the sample space for rolling 2 fair dice. The first roll, we've got, you could get a 1, 2, 3, 4, or 5, the top line. Then in the second roll, with that 1, you could get a 1, 2, 3, 4, or 5, or 6. With the 2, same thing. 3, same thing, and so on. So I'm just looking at the ones where we've got a total of 2 or a total of 5. Well, there are 36 total possibilities, and I didn't write them all, but you can get a 1, a 2, a 3, 4, 5, or 6 on the first roll. And then I'm going to do a table down the side. I would have 1, 2, 3, 4, 5, or 6 for the second roll, which would be the second line. And if I fill in the table, you'd have all the possibilities. So it's a 6 by 6 table, so there'll be 36 possibilities. Okay, and then if we look at the ones where you can roll, or you can get a sum of 2, well, the only one where you can get a sum of 2 is 1 and 1. Okay, so that adds up to 2. and you would lose. There are a few that total 5. So 1 and 4 totals 5. 2 and 3 totals 5. 3 and 2 totals 5, or 4 and 1 totals 5. So there are 1, 2, 3, 4 ways that could happen. So let's take a look then. All right, so I've got those I showed you on the tree diagram. You can rewind if you want to see that again, but you got a 1, 4, 2, 3, 3, 2, or 4, 1. So the probability of total of 5 is 4 out of 36. The probability of a total of 2, there's only 1, so that would be 1 out of 36. So if we're going to say you either win or lose, and that's what's going to happen if the game ends, then the game ends if you win here. No, wait a minute, total, yeah, and the game ends if you lose here, if it's a total of 2. So we know that that's going to be total of 5 probability is going to be 436. Total of 2 is 136. So together that is 536, or about 13.9, almost 14%. Now, the reason I didn't reduce this right away is because I knew I was going to have to add them, so I kept common denominators to make them easier to add. And you hear my dog out there, that's Rudy. I had to get him out of the house because he kept barking. And then, of course, somebody's walking a dog and starts barking at that. So apologize on that. But tomorrow when you come in, how about, don't tell anybody, but how about if you, let me think here. Let's think of something funny. Oh, is there anything funny you could do? How about you are going to take a dry erase marker and hand it to me. Just hand me a dry erase marker that's on the dry erase board. If I run out of dry erase markers, you can go get Smartboard, the fake markers. Have a good one. See ya.